networks are constructed last time. Okay, so that was, you should remember this example, how you pick an order and introduce them, and the useful thing is if you happen to know the domain, it's useful to introduce the nodes in the causal order. Okay, and there are two reasons for that. One is, of course, that actually causal order tends to have fewer edges. Okay, and of course that means that you need to assess fewer probabilities. And secondly, it turns out that causal probabilities are easier to assess than diagnostic probabilities. They tend to be more robust. So, remember that, from a medical point of view, a causal probability would be of the type, what is the probability that you will have runny nose if you have flu? That's causal probability. The diagnostic probability is what's the probability that you'll have flu if you have runny nose? Okay, the interesting thing is the percentage of people with runny nose, percentage of people suffering from flu who have runny nose is about the same whether it's in Tempe or New York or in Taipei or in Delhi. Okay, whereas on the other hand, the probability of flu given runny nose very much depends on if there is a flu epidemic going on. Suppose Tempe there is no flu epidemic, but suppose in Tucson there is a flu epidemic. Then a random person with runny nose in Tempe is less likely to be suffering from flu than in Tucson for those few days of epidemic flu. And then again it will change. So the point I'm trying to make is causal probabilities are more robust. So if you have to set up an experiment to get these numbers, right? So you have to get this, if you want to assess this, either you will ask people, tell me what do you think is this number. Okay, and the other one is you actually set up a systematic frequency experiment. Okay, so there you'll get a bunch of people who you know have flu, and see what percentage of them have runny nose. And if you are assessing it that way, then this number is likely to sort of remain the same, irrespective of the season. Whereas this number is likely to change depending on the season and depending on the place. Okay, this is why doctors actually have probabilities written in this order rather in their textbooks, in essence, rather than this order. Okay. One other thing that actually I came very close to, and so I should mention it, is I said if you needed these probabilities, you could either just ask somebody or set up an experiment. Now, if you ask somebody, how are they supposed to know? This gets you to one of the most interesting sort of schisms in statistics. Frequentist versus Bayesian. Outside of this class, you'll keep hearing Bayesian statistics, and you'll keep hearing it. That's like they're working quite well nowadays. And the reason Bayesian statistics are interesting is not because of Bayes' rule, which will work any day. The point about Bayesian statistics is frequentists say that a probability is a probability only if you actually run a frequency experiment. Okay, for every number here, you should have set up an experiment, and as the number of experiments tends to infinity, the limiting ratio is the probability. That's the definition. And this is the definition that you happen to know, right? I mean, this is the one that when somebody said, when you thought, what is the probability that a die, when I toss a die, it'll come 6. It's 1/6. What's the probability that it'll come even? 1/3. All these things is because you assume that you can set up frequency experiments and get these numbers. Okay, now some probabilities are like that, but I want to ask the following probability. What's the probability that Einstein was drinking herbal tea at 4 p.m. on 1937 April 4th? What's the probability? Okay. Now, many of you are willing to give some, bet. I mean, it's like you take bets. You give a bet. You give a probability. I think Einstein, the guy is from Germany. Germans don't drink that much teas to begin with. Maybe he's not drinking tea. So I'll say look. Okay, you made up this whole probability up. Did you set up an actual frequency experiment? No. First of all, how do you set up a frequency experiment for that particular question? Unless you really are a big believer in the Groundhog Day, the movie, where Einstein gets to live on that particular day many, many times. And so how many of those days did he actually wind up drinking tea at 4 o'clock? Did you understand what I'm saying? So there are questions for which you want to assign probabilities, but you can't see any reasonable way you can actually conduct a frequency experiment. In such cases, frequentists will say that's not part of probability theory. We shouldn't be talking about it. Bayesians will say, no, I'll make up a number. I'll give you a number to you. So Bayesians feel that they have personal probabilities. So, for example, a Bayesian can say, if I say, I'm tossing a coin, what do you think is, the chance of it coming heads? A frequentist will actually, do an actual testing and figure out what the probability is. A Bayesian will say, since anyway I was making up, probabilities for Einstein drinking tea, I'll make a probability for this too. I'll say 0.3. I'll say 0.7. I'll say 0.4. Whatever I feel like. Okay? This basically means the word probability is now personalized. Like a 21st century probability. Everybody gets to make up their own probabilities. However, this is exactly the point. This is why, remember last class I said, P of A or B, how do you write this? We write this normally as P of A plus P of B minus P of A and B. Right? Okay, and I said, how do we know that this is actually a reasonable thing to do? Well, from a frequentist point of view, it's a pretty reasonable thing to do. From a Bayesian point of view, the interesting question is, what if a Bayesian wants to be really very personalized? They want to make up any probability, any which way they want. So they want to provide a probability number for this, one for this, one for this, one for this. If they do that, then obviously this rule won't work, right? That's when you have to say, well, yes, I understand, you can have your belief system. But if your belief system is inconsistent with this rule, then I'll set up a bet where you lose all your money. Okay? So as much as you would like to think that it's a God-given right to believe whatever you want, okay, you can actually lose all your money, if you don't believe this rule. I mean, if your probabilities don't correspond to this rule. Okay, so this is actually a very big distinction in statistics that you may not have recognized formally before. Okay, because you lived in both worlds. On one hand, you always thought of probabilities as, well, frequencies. But on the other hand, people always ask you, what do you think is the probability that I will be wearing a red shirt tomorrow? How the heck am I supposed to set up a frequency experiment for this? And yet, do you stop saying, no, I won't give any probabilities? No, you will give a probability. So in that case, you're being Bayesian. Okay? The reason these networks are actually called Bayes networks is partly also because I couldn't care less as to how you got these numbers, those numbers. You could make them up out of whole cloth. All I will do is, once you put those numbers there, I'll make sure that your inference is consistent with respect to the numbers you put. I will never ask you enough questions to get you into inconsistency. I will never, for example, ask you both P of A and P of B and P of A and B and P of A are B. Because if I ask you all those 4 numbers, you may or may not have satisfied this rule. Okay? And similarly, I don't ask you both probability of burglary and probability of not burglary. Because you might take personalization too much to the extreme and say, oh, probability of burglary is 0.3, probability of not burglary is 0.2. Then I say, what the heck is the 0.5 going on? I don't know, I don't feel like that part of the world. Okay? So I won't let you do that. I won't even let you open your mouth and tell me what is P of not burglary. I'll just say, what is probability of burglary? You make up your number. I'll assume 1 minus that is what you believe is probability of not burglary. One of the most beautiful things here is, by not asking questions other than the required number, I will always be able to give you a consistent joint distribution. You see what I'm saying? A consistent joint distribution will always be given to you. And these numbers, I don't actually take a stance in this course as to how they were arrived at. You could have asked your expert, you could have asked, you could have just thought about it yourself and say, I feel like P of D given not B and not A is like 0.2. Just put it there. You never have to worry, maybe I'll get into circular reasoning. You won't get into circular reasoning because I'll never ask you any question that will get you into circular reasoning. You see what I'm saying? So if you allow people personal freedoms, then there's always this question as to how do you make sure that they don't basically infringe on the laws of consistency. Well, this is how I do it. Okay, so we actually don't really care in this course. As far as this particular part is concerned, really, we could be getting the probabilities as a frequentist probability or a Bayesian probability. In fact, Bayesian is a more general case. So Bayesians can say, well, I feel personally like actually conducting a frequency experiment today. Or I don't feel like doing that, I'll just give a number. Both are fine for Bayesians. Frequentists, on the other hand, must conduct an experiment, in essence. Any questions on this? See, this is actually, that's the real reason for calling these Bayesian networks. It will become clearer later on. But as far as we're concerned, these probabilities are just either assessed or are given to you by somebody. And it's just their personal opinion. The interesting question is, if you believe these numbers, then you must believe whatever this joint distribution says. So many a time people will actually believe A, and they'll also believe A implies B, and they would like to delude themselves into thinking B still may not happen. You see what I'm saying? But you are actually making it very clear to them. Since you believe A and you believe A and B, A implies B, you actually now have B. And similarly, since you believe these probabilities, according to the consistent joint distribution that they define, each probabilistic query has a particular answer. And you cannot, you can't just say, is it more likely that if John calls, that alarm actually occurred, or not likely that alarm occurred? You don't get a chance to figure that out. I'm sorry, no, not that way. Alarm and John actually are in this table itself. Suppose if there is an earthquake, is it more likely that John calls or less likely that John calls? It's not written in this table, but it's predestined. Because Pj given E can be computed uniquely from the joint distribution that is defined here. So you don't have any freedom there. Your freedom went away when you filled up these tables. After that, you use laws of probability. Okay? So that's the thing about Bayesian probabilities. Okay? One other thing that I'm going to talk about, that basically much of today's class is going to sort of make sure that the semantics of this network structure sort of sink in. Okay, one thing we figured out in the very beginning of today's class is if I give a arbitrary configuration of the network, you will be able to tell how many numbers are needed. Okay? And similarly, you will also be able to tell if I ask you any given joint probability distribution entry, you can compute it. And from that, and from the last class where we showed to ourselves that if you give me a joint probability distribution, I'll be able to compute any possible probabilistic vary uniquely, right? So that means the moment I know the joint probability distribution, I know how to answer any question. Mathematically, it's just determined. It's just a question of computationally how long will it take is a different issue. Okay? The other thing was we were very much interested in this example at least of trying to reduce the number of numbers that we will ask the expert to give us or we go into the world and assess. Okay? Now, interestingly, actually, and this is something that comes up in the project that you'll be doing too. By the way, the third project, which will be given on Thursday, right after Thursday, would be essentially kind of a Bayes network modeling project. We'll give you like a scenario, and then we'll give you a link to a Java applet for Bayes networks. You model the scenario, and then you check various inferences. Okay, and one of the interesting questions is, suppose basically I know the joint probability distribution over these 5 variables. Suppose I happen to know. So I am the expert, I know. And you get to write the network, and then you come and ask me, Rao, can you please tell me this number, this number, this number? Since I have the joint distribution, I'll give you the number. Right? I can give you these numbers, or these numbers, or these numbers. What's interesting is all these sets of numbers will specify exactly the joint distribution I have in my head. You see what I'm saying? So in fact, what actually is happening is one way of thinking about all these graphical models is that they are factorizing the joint distribution. Suppose I thought of a number, okay, suppose in my head I have a number, let's see, what would be a good composite number, 32. Okay, this guy comes and asks me, give me some numbers, so that I'll multiply, I'll get you 32. I'll give him 16 and 2. This guy asks me, I'll give him 5 2s. This guy asks me, I'll give him a 4 and 8. All of them have different numbers. But if they multiply 4 and 8, they get 32. If he multiplies 16 and 2, he'll get 32. If he multiplies all 5 2s, he'll get 32. So they're all essentially computing my compound number by their factors. That's the intuition Bayes networks are actually using. The bigger joint distribution is being computed in terms of multiplication of these smaller tables. So you can think of these as factors. Okay? Here you part this into 1, 2, 3, 4 factors, and the biggest factor, the table size, is the size of the factor. Here is a big factor suddenly. Okay? In this particular case, essentially, you have bigger factors, basically, because the number of numbers you gave is as many as the numbers I actually had in the original joint distribution. You see what I'm saying? So it's just that if you had asked me these questions, I would have given you fewer numbers, and that would still get you back to my original joint distribution. This is something that you will do in the project. Yes.
So is the relation is it asymmetric? Like if you know the joint distribution, then you can assign probabilities to any of these models. But if your model is not correct, then from those numbers you may not be able to go back to your joint distribution. Suppose in that model you are missing some connections. So if you calculate the original joint distribution.
No, so the question of connections is a very interesting one. Okay, so that's a good point. If you don't put connections, that means you were answering these questions wrongly. If you do that, then all bets are off. But by the way, one way you can actually check whether or not this is the case, is in fact, if I have the joint distribution, right? I have the full joint distribution. I'm ready to play 20 questions with you. You can ask me a question, I'll give you an answer. You can ask this question also. You can ask, what is Pj given M? And what is P of J? And if they're the same, then J is independent. J is independent of M. You see what I'm saying? But the trick that we actually deal with in real life is there is nobody who knows the entire joint distribution. So biases matter, and that we will talk about when we talk about learning these structures from just the data. That's a very interesting problem altogether. But if you happen to know the true joint distribution, then you can't make mistakes, because you can ask these questions too. If your rich uncle knows true joint distribution and is willing to play 20 questions with you, you will never make mistakes. It's a very good question, by the way. Okay. So anyway, then we are sort of interested in factorizing a joint distribution, and you want the factor sizes to be small. That's why we like this more than this. Because in this case, the biggest factor is basically, the biggest factor here is what? 1, 2, 3, 4. So 2 power 4 size. Right? The biggest factor is 2 power 4 size. Okay. So whereas here the biggest factor is only, where does the biggest factor occur? Here, alarm, and it's only 2 power 2 size. So the trick is to write networks such that no node has too many parents. No node has too many parents. Okay, now here's my question. Suppose I have n nodes . N nodes here, M nodes here. Suppose it turns out that actually, somehow some aggregate property of these M nodes winds up affecting each of these M nodes. For example, let's say the max value of these M nodes affects each of the M nodes here, or the average of these M nodes affects the values of these nodes here. That's the domain theory. But you only have n nodes here, m nodes here. So if I ask you, this guy have a link from here to here, would you say yes or no? Yeah, because max does depend on this guy too. Average does depend on this guy too. So does it have a link from here? Yeah. About here? Yeah. About here? Yes. About everybody? Yes. So how big is this guy's conditional probability table? It's 2 power n size. How many nodes are here? M nodes. So how many probabilities do you need here? M times 2 power n probabilities, assuming Boolean for now. Okay, plus of course, each of these guys also need probabilities. And so there are, how many probabilities do you need for that? N. So I need n plus m times 2 power n probabilities to provide this network. But I told you the domain theory. The domain theory is that not each of these guys are actually affecting these guys through a sort of an intermediate statistic, like a max, or a sum, or an average. So what if I introduce a middle node? This one is the, let's say, max node or the average node or whatever. Right? Clearly, this node is going to be affected by all of the n nodes above, right? So you need 2 power n numbers here. But then each of these nodes are only affected by this node. Do you see what I'm saying? Okay? So what do I do then? Essentially, in this green thing, I will still need at the top m probabilities. For the green node, I will need 2 power n probabilities. And for each of these, I need 2 probabilities. One when the green node is, I'm assuming again Boolean. Okay, one when the green node is true, what is the probability that this will be true? When the green is false, what's the probability that this will be true? Okay, and there are m of those, so 2m. Okay, so what did I do here? Which is bigger? Which number would you rather have? The green one. Right, I wrote it in green. Right, it must be good. Okay, so this is really small number compared to this, because this one has m times 2 power n. This is just 2 times m, and there's only 1 2 power n here. I did this by making an intermediate concept. It may well be that these guys are, let's say, the diseases. These guys are the symptoms. Who is this guy? From a domain point of view, who is this guy? It's not a disease. It's not a symptom. It's something that I just made up. But it's an intermediate concept. I made it up expressly to make the network sparse. If you make the network sparse, the number of numbers you need will be reduced. Do you think you do this in real life? Do you think you do this in real life? Have you heard of something called GPA? What the heck is GPA? Right? I mean, really what you should say is what your job would look like would depend on what you did in each of the homeworks in all your life. Right? Each of the exam questions in all your life. Each of the participation credits you got all your life. And so you'll have a really nice, happy, if you put each of these as variables, then you have job, and it's now handling a humongous number of parents. So what do? We say, well, really what matters is your GPA. GPA does depend on everything else, but then your job sort of depends only on the GPA. I mean, to the extent it does. Okay, so I invented a concept called GPA, which sort of made the network sparse. Of course, after you invent it, becomes real. So now you no longer are interested in homeworks, you're not interested in jobs, you're interested only in GPA. Right? That's how we invent things and they become real process. So in this particular case, I invented this max or average node, which didn't exist before. What's interesting is, oftentimes, so this is this example. Whatever I wrote here is written again in print here. Okay, I'll skip over it. Here is actually a real network for a somewhat more real network for automobile diagnosis. Instead of patient diagnosis, automobile diagnosis. Okay, so the green things are testable variables. What's the age of the battery? What's the battery meter saying? Are the lights working? Is the aisle light on? Is the gas gauge showing empty? Things like that. Those are testable variables. Okay, and then the yellow ones, the orange ones apparently. I don't know, they look yellow to me, but anyway, these orangish yellow ones, they are all fix this variable. This is broken. So for example, no oil, okay, or no gas, our fuel line is blocked, our starter is broken, our fan belt is broken, our alternator is broken, our battery is dead. Battery is dead. Okay? Now, what is interesting is I have these gray nodes, and those are syndromes. In medical terminology, you have diseases, you have symptoms, you have syndromes. The syndromes are intermediate nodes. Okay, so for example, no charging is an intermediate concept. No charging can happen either because alternator is broken or because fan belt is broken. So when no charging happens, then either you have to fix this or fix this. When no charging happens and battery is dead, then battery could be flat. That's another intermediate concept here. Okay? And notice that this network actually is written, to the extent you understand automobile mechanics, it's written in the causal direction, right? Because no oil is going to symptoms. Okay? right? And this too actually is causal. Battery age affects whether a battery is going to be dead or not. And if battery is dead, then that would be affecting battery meter. Battery dead or not affects battery meter. That's capturing that. So this is a Bayes network. And a little simple thing that you can do at home is count how many probabilities, assuming these are all Boolean, which they are not actually. If they're all Boolean, how many probabilities do you need? You should be able to read this off and say how many probabilities you need. And more interestingly here, I put this no charging here because if I don't put this no charging here, then every node, every edge coming from no charging, now if I remove this from graph, in a graph theory, if you remove the vertex, then the way you do it is everybody who is going here will just go to wherever the other net edge is going. Okay, so since no charging is going to battery and alternator broken is going to battery, alternator charge broken is going to no charging, you put a link from here. You also put a link from here to here. So suddenly now this guy has 3 parents. And in fact, this 2, worse yet, this 2 is an intermediate node. So if you remove this, then everything goes crazy because now these guys will have 3 parents each. You see what I'm saying? So one way you reduce the size of the network is by introducing hidden variables. Hidden in the sense that in your obvious understanding of the domain, you know about sensors in the automobile, and you know about specific things that can go wrong with the automobile. These intermediate things, you don't have any clue. But you made them up, and if you made them, actually, the structure actually reduced in size. The number of probabilities you needed reduced in size. Now, what's interesting is, suppose you came into this world, and from Mars, where they don't have automobiles, and I just gave you a humongous amount of data. Now, the data that I'll give you won't have these numbers, anything about these, because these are made-up concepts. So my data will have sensor values, will have disease values. And you're trying to learn the Bayes network from that. I understand today I'm not doing that. I will do it when I get to machine learning. Okay? But the interesting part is introducing hidden variables makes learning harder. Okay? Because those hidden variables are not present in the data. So it gives you too much freedom. What stops you from making up all sorts of crazy, nonsensical hidden variables, such as the black cat came in front of you, and that might somehow be connected to anything bad going on to you. Okay? So any random, this at least in the data, these are not in the data. So you have too much freedom as to how to make these up. And so there's too many different networks that you can learn. Which one is the right network? You see what I'm saying? And that's a hard problem. In general, machine learning is hard, and this, in one version of that is deciding which intermediate concepts have to be put in the network. It's not obvious. But you know why you want to do that, right? You want to do that because if you put intermediate concept, you need to ask for fewer numbers. And in fact, there is this idea that we'll talk about when I get to learning called overfitting, which is if you ask too many numbers for writing this network, there may not be enough data to support assessment of all those numbers with any possible accuracy. Okay? And to avoid overfitting in some sense, even during learning, you may want to do these intermediate concepts. And from an inference point of view, they are good because, again, essentially, specification, mostly they make sense from the specification point of view. They're good because when they are there, the number of numbers that you need to assess reduces. And each of the numbers is a number that a learner has to learn. The fewer numbers a learner has to learn from the same given data, the better off it is. Okay, that's the deeper point. Okay, any questions on this? Okay, so I showed you essentially a new way of reducing the size of the network. Apart from just the topology, you can introduce new nodes and then that way reduce the size of the network. Okay, right? And that's what experts are for. They're supposed to make up these intermediate concepts. And if you're doing learning, God help you, because you need to figure out how to make these. And even if you were to make this, it won't come with a name, no charging on it. It'll be node number 78. And over a period of time, you will realize that node number 78 seems to have the semantics of no charging. Or whatever you want to say in Martian, for saying the same thing. That's how learning is. Okay, but in this case, we happen to, somebody knows the domain and they told you put these things in. Okay. One other interesting issue, another way of reducing the size of the network is, here, when in all the things we have done till now, I'm basically assuming for each node, I provide a conditional probability table. Really what I need is a conditional probability distribution. Okay? And I just wrote the distribution down in an extensional format. I said, if the value of the parent is this, if the valuation of the parents are this, this, and this, then the probability that this guy will be true is this. Okay, think about the following thing. Suppose I have a couple of continuous variables in my network. We aren't talking about them right now. But suppose, for a minute, think about continuous variables. If you have a continuous variable, how big would be the CPT? Extensional form CPT. What? Infinite. Did you ever use continuous variables in statistics before you came to this class? Did you ever write tables for them? What did you do? You used specific parameterized distributions. Okay? It's way too hard to figure out exactly what is the probability that a variable takes this value versus this value versus this value versus this value when it's a continuous variable. It can take infinite number of values. For each of them, I need to know the probability. So what do? I'll throw in a distribution. If we like throwing, most of us tend to throw in the bell distribution, bell shape, which is the normal distribution. And it has beautiful theory behind it. The theory of normal distribution is the central limit theorem. If in fact what you are observing is actually some sort of a sum of many, many independent variables, all of which are distributed at different distributions, then the sum winds up being distributed as normal distribution, Gaussian distribution. Okay, there's a reason. But on the other hand, eventually, most people, when people come and ask me, do you curve the exam? Right? And some of you ask me, and I say, yeah. What do you think that means? You must be thinking something about curving. And most people, curving essentially means that you assume a normal distribution of marks in the class. And then, because normal distribution has a unique, it's a unimodal distribution. It has highest probability at the mean. And so you assume that's the average, some, sigma away from the average is kind of B, one more sigma away is maybe A, and so on. Right? In fact, I think actually the picture that people tend to draw is something like this, right? This is the average mark in the class, and then you sort of throw this as your C, and maybe this as your B, and this as your A, this as your A plus, this as your God. Right? You teach the class, I don't want to teach it. Okay. Right? And that's why actually you call these kids, if you call somebody a 6 sigma kid, right? What does that mean? They are either 6 sigma, they're basically 6 sigmas away from the average. Okay? And this distribution turns out to be an exponential distribution.
you on the bad side also.
Yes. So I just say Six Sigma kid and not show any expressions. And you're supposed to figure out, what I meant. But a Six Sigma kid is truly on the bad side or truly on the good side. Most people normally, since we are polite bunch of people, we only say it when we have it on this side. Okay. By the way, the interesting thing about this particular distribution, it's not actually for this class, but it's an exponential distribution. Okay. And an exponential distribution is interesting because rare is quite rare. If I really believed that the marks of the class are distributed uniformly, Six Sigma kid is just as much of a bozo as anybody else. There's no difference. If the marks are distributed polynomially, then Six Sigma kid is not as rare as Six Sigma kid would be in the exponential distribution. Mostly people just assume, if you say distribution, they assume Gaussian for good reasons. Okay? And in the case of Gaussian distributions, you basically, it's very rare, to get away from the mean. But the bigger point that we are talking about this here is we could do continuous distributions. That's how we actually handled. So the CPT now would be, some example, I would say, what is the probability of A given B? It might be a conditional Gaussian, whose mean would be the current value of B. And the variance is based on B. So A is now varying, value of A is varying with respect to the value of B. Maybe it's centered around B, and then it has some variance around it. That's how you get by. You don't write an actual CPT. When you do that, there are infinite probabilities here, right? How many numbers do I need to give to tell you a Gaussian distribution? 2. So I went from infinite numbers to 2 numbers. You see what I'm saying? And if you are into reducing the numbers, then that's a great way of doing it. Parameterize the distribution. Now, of course, the problem with the parameterization is, do you guys really believe that your marks in the class are always normally distributed? Do you believe this? No. It never actually, I drew these curves and it never looks like normal. I just put a normal on it. And then I ignore it. In my case, I completely ignore it, but that's a different story. People who want to believe it's a normal distribution, they need a really, really large sample size. And even then, it's kind of iffy as to whether or not the distribution is truly normal. What did you do? You just assumed that let the distribution be normal. I would just assume that the distribution is normal. If it is, then what's the best mu and sigma? Mean and variance. So this is approximating the true distribution, which would require infinite numbers to write down. In the case of continuous, essentially, that's the only thing you can do. In the case of discrete, we thought we could get away with actually writing the tables, but the tables can get quite large if, in fact, the variables have too many values. Right? And so, once again, even for discrete variables, we will wind up considering parameterized distributions. There are discrete distributions. Give me one name. What? Poisson and binomial are distributions that are discrete distributions. Okay? And Poisson actually looks almost like normal. It just has one parameter. Okay? So here is, so the interesting thing basically that this slide is trying to say is one way of reducing the numbers is parameterize the relation between the parents and the child. When you give a table, any possible relation can be captured in that table. If you give a formula, that formula says this is the relation. If you give a form of the formula, then you are saying the relation can only be either Gaussian or uniform or something like that. Either way, because you make that jump and saying thou shalt have the following kind of relation, you only need fewer numbers to actually specify the entire conditional distribution. Okay, so one example of conditional distributions being parameterized is Bayes networks can actually have certain deterministic nodes. There could be nodes which are deterministically connected to each other. By the way, that sort of would partially answer the question I asked on thinking cap. What happened to dependencies? They're there in deterministic cases too. Okay, so for example, I could have Boolean functions. So North American could be a node which is really Canadian or US or Mexican. That's what the relationship is. So if I just write this, you can convert this into a CPT now. Right? You see what I'm saying? That's what you can do. And then you could also have, if it's a continuous variable, you can do the normal distribution kind of thing. But we are talking about discrete, and I said Poisson is one, but here is another more useful one called noisy R distribution. In many cases, so here are a bunch of people who are standing in front of you, and you did something wrong. Maybe you didn't complete the homework on time. I got a firing squad. And basically, they didn't collude. The good thing is all of them are independent. They're independently trying to shoot you. Okay? Right? So, the probability that you will live after the shooting is over depends on how good of a shooter they are, clearly. You really would hope that none of them are good shooters. But if you have 1,000 people, 999 of them are people like me, and then one guy is wired up, you're dead. Because that guy never misses, apparently. At least if you see the Hollywood movies. I wasn't there. But he's a very good shooter. So if one guy shoots, that's enough for you. Right? So in a noisy R distribution, the expectation is there are multiple causes that can be causing this symptom. And they can all be independently causing this symptom. So you can get runny nose from flu. You can get runny nose from allergy. You can get runny nose from dust, etc., etc. Now, if allergy and flu are not correlated, and allergy and dust are not correlated, let's say, then there are actually 3 different shooters trying to, shoot runny nose into you, essentially. Okay? And the distribution that I will capture, I would say basically, I would not have a runny nose only if none of the causes are able to give me runny nose. If all of them fail. So in the case of shooting, I will survive if every one of these guys miss. And if any one of them doesn't miss, curtains for me. Okay? So the numbers I need, so for example, if I have, another example here is cold, flu, and malaria can all cause fever. Fever is a symptom. Right? Imagine that cold, flu, and malaria, if you assume that cold, flu, and malaria are independent, and they are independently causing the fever, then the assumptions you're making are 1, if all of them are false, fever probability is 0. 0.1. And then the other numbers you need is, if I just have malaria, what is the probability that I won't get fever? And if I just have flu, what is the probability that I won't get fever? And if I just have one more, just T alone, this one, okay, which is cold alone, what's the probability that I won't get fever? This is basically like saying here is gunner 1, gunner 2, gunner 3. If only gunner 1 is shooting, what's the probability that she will miss? Only gunner 2 is shooting, what's the probability that she will miss? Only gunner 3 is shooting, what's the probability that she will miss? If I got those 3 numbers, then I know the probability that all 3 of them miss, because they're independent. So then I know the probability of my living is 1 minus that multiplication. Do you see what I'm saying? So I'm able to actually give, in this particular case, I have 3 parents. So I need essentially 2 power 3 or 8 numbers. But I only gave you 4 numbers. I gave you this. Basically, this is part of the assumption. That means if none of the parents are true, then the fever's probability being true is 0. And then I gave for each one parent being true, what's the probability that the fever will be false. Given that, I can compute every other number. because of my assumption of noisierness. And oftentimes, basically, when you have multiple parents for a node, and you are about to go and ask the expert, give me the big CPT, you might say, let me just assume that it's a noisier. Then I can ask the expert fewer questions. If you're wrong, then obviously it's a bad assumption. But at least it reduces the number of numbers you need to get. The other interesting thing is you ask too many questions to an expert, they're likely to give you wrong answers because of just irritation. So getting a large number of bad numbers versus small number of correct numbers but for bad theory, which one is right? It's not obvious. Okay, so what do you do in this case? So for example, if I need to compute the probability that I will have fever when I have no cold and I do have flu and I have malaria. For that, what do? First, I need to check the probability that I will not have fever when flu and malaria are true. That's 0.2 times 0.1. Because 0.2 times 0.1. So that's the probability that I won't have flu. 1 minus that is the probability that I'll have. Okay? So by using parameterized distributions in the network, I can again reduce the number of numbers I need to access. Okay, so that's the art. So we talked about first get the topology right. If you can't get the topology right, then if the topology is not enough to reduce the numbers, then introduce hidden variables. If the hidden variables are not able to reduce the numbers, sometimes, you can do all of them too. Use parameterized distributions. When you use parameterized distributions, you're making big meta assumptions about the specific form of relation between the parents and the child. And so that would reduce the constraints, the kind of CPTs you can actually write. And all of those will have additional structure. So they can be specified with fewer numbers. So if I ask you, given a network like this, how many numbers are needed? Whatever you computed, that's only the upper bound. Because then I can continue and say, well, I think this is an OICR distribution. That'll reduce the numbers again. If you put additional assumptions, the numbers will reduce again. Any questions? Okay. So what I'm going to do next, the last part of this class today, is actually go and talk about the notion of independence assumptions that are present in the Bayes network. And next class, we'll start talking about inference with them. Okay. Now, before I even do this, remember that if you don't know anything else, if I give you a network, you know at least how to do inference one way. Right? You know how to compute the joint. Once you compute the joint, you can answer any query. So you know one way at least. What we'll do next class is whether you can do better than that. And in the next class, we'll first point that, in fact, in the worst case, you can't do any better, because in the worst case, Bayes network inference is at least as hard as model finding for propositional logic, which is NP-complete. And it turns out actually Bayes network inference is harder because it actually counts the models. It's not just checking whether there's a model, but it counts how many models are there. So, if you are into the terminology of complexity theory, it's sharply complete. It counts models, okay, which is kind of considered to be harder than NP-complete. And so then having convinced ourselves that we won't expect to do well in the worst case, we'll start looking for, on the average, good algorithms. And that's what we'll do next class and probably class after. But today's class, for the next 10 minutes, what I want to do is go back to this idea of conditional independence assertions. Remember, we mentioned that independence assertions are extremely important, and that's what actually reduces the joint distribution. And of course, Bayes network captures some independence assertions. And we took a very tell me just how much I need to know kind of an approach. And the most useful thing you used is a node is independent of all its non-descendants given its immediate parents. But generally, I might want to ask you a random questions like this. is the set of variable x. X is a set of variables, not necessarily a single variable. Is the set of variables x independent of the set of variables y given evidence on a set of variables z? That's what I want to know. If this is true, if in fact this independence assertion is true, then it has a lot of ramifications. For example, if x is independent of y given z, then p of x and y given z is p of x given z times p of y given z. So you need fewer numbers. And another way of writing it is p of x given y and z is p of just x given z. Okay? And p of y given x and z is just p of y given z. And it's these independence assertions that will allow you to, factorize a joint distribution into smaller probabilities. Okay? So that's the basic theory behind why the independence assertions, why the conditional independence assertions are useful. Okay, now, in the case of Bayes networks, we already knew this much. Look at this guy. This guy, the one independence assertion, one family of independence assertions we knew is a node is independent of any subset of non-descendant nodes given its immediate evidence on its immediate parents. So I get to write, this picture is essentially telling me that, there's a blanket here. Okay? Now, I can say X is independent of any set of nodes outside the blanket given these two nodes, given the nodes on the blanket. Given the nodes on the blanket. It's sort of, you put a blanket so that you will keep elements at bay, right? Okay, so these guys can't affect X. These guys can't affect X if you give these. But this blanket isn't particularly good, right? Because there's a huge hole in the bottom. So cold air is coming from here, right? So it's not a true blanket because what if I give these? I mean, is X independent of Y given U1 and U2? No, it's not actually. Okay? So there is a better definition. The better definition is the Markov blanket. And this was, this is Linus with his blanket, for those of you who remember peanuts. Okay? This is a security blanket for X. And security blanket for X is its parents, its children, and the 21st century nuclear family, its children's other parents. Right? I mean, I think there is some sort of a ABC sitcom going on like this, right? So essentially, you have your children, their other parents, and your own parents. That is the nuclear family. If you give everybody in this blanket, then you are independent of everybody else outside the blanket. And that's more than this can say. But even here, I still did not answer specific questions, such as if I give you a subset X and a subset Y and a subset Z, is X independent of Y given Z? Okay? And in fact, these two are really sort of falling from a more deeper definition of conditional independences. To understand true definition of conditional independence assertions, you need to understand paths between nodes. Okay? And the basic idea is I would try to say that X is independent of Y given evidence nodes E if any path going from a node in X to a node in Y is blocked by the evidence node E. That's what blanket is supposed to do. Any cold air coming from here to me is blocked by my blanket. Right? Nice analogy. The question, of course, is how does blocking work? Okay? And to understand blocking, we will consider only three different types of paths. So look at this picture. I have X nodes here. I have Y nodes here. I have the Z nodes, which are the evidence nodes. Those are the nodes on which I gave you the information. A conditional independence is always X is independent of Y given evidence on Z. Now, if you want to say X is always independent of Y no matter what Z is, that basically means this set is empty. That's all. Okay. Now, my question then is, there are paths from X node to Y node. So here is a path which goes from X to Y. Here is another path which goes from X to Y. Here is another path which goes from X to Y. I have to consider each of the paths and do the following thing. Ignore the directionality of the path except the arrows when they come into Z. So it doesn't really matter what the directionality here is. That's why I didn't tell you the arrow here. In fact, every node, every arrow in Bayes network, every edge in Bayes network is an arrow. But I didn't put an arrow here because I don't care about that. We ignore the directionality of the arrows except when you are at the evidence node. Then there are only three cases. Either the path is coming into Z and going out, or from Z the path is going out both directions, okay? Or into Z both paths are coming in. Do you see what I'm saying? Only those three cases, nothing else. Of course, there are all sorts of things can be going on here. All I care about is at the node C. These can have, you can have names here. Here, this is a causal chain. Somehow X is causing something which is causing Z, which is causing this. It's a causal chain. Okay? So X causes Y through Z. And so if Z is blocked, then that particular path is blocked. So if you know Z, then essentially that path is blocked. The other is the common cause. Z causes both this guy and this guy. And so if I tell you Z, then this is independent of this. So cavity causes both toothache and catch. And so if I tell you that you have a cavity, then toothache is independent of catch. Okay? So in these two cases, the paths are blocked for simple reasons. In this case, the path is going through Z, one direction to another direction. Okay, that's a causal path. And then you can also have it this way. That will be fine too. But this one is different. Here, it's going. This one is going this way. This one is going this way. So that's causation path. In both those cases, if this node is in the evidence, then these paths are blocked. The third case is interesting. The third case, Z has both paths incident on it. At this point, this is like burglary and earthquake are incident on alarm. Okay, so normally if I didn't tell you anything about alarm, is burglary independent of earthquake? Yeah. Why should people pick the day of earthquake to do burglary or vice versa? But if I tell you alarm is going off, is burglary independent of earthquake? Yes, because that's explaining away. If alarm is going off and I told you burglary occurred, then you don't need the earthquake to occur. And similarly, if alarm is going off and earthquake occurred, then similarly you don't need the burglary to occur. So they become dependent because you know alarm. So here they became independent because you knew the evidence, Z. Here they will become dependent if you know this evidence. Okay? Not only that, in fact, if I tell you John called, so if I tell you before, I don't know anything, do you think burglary is independent of earthquake? You'll say yeah. By the way, John just called. Is burglary independent of earthquake? No. Because if John called and you know burglary is true, then earthquake is less true. And if John called and you know earthquake is true, burglary is less true. So in some sense, John calls is playing the same role here as alarm. And if you know any of these guys, then these two guys become dependent. Okay? And so basically the three cases that we say are x and y are independent given E if for every path that goes from x to y via E, via some nodes, right? If any path, at the evidence, if in fact the path is going unidirectionally and you know Z, then that path is blocked. I mean, at least one node as evidence, that path is blocked. Okay? If it's going from the evidence both sides and you know one such node, again the path is blocked. And if it is going into a node, then if you either know that node or any of its descendants, then the path is not blocked. Or, for it to be blocked, you should not know Z or any of its children. That explains all conditional independence assertions. So actually I put some examples here. I won't go through it because we are out of time. It turns out you have to convince yourself, and next class this would be again tested, without actual penalty. You should be able to convince yourself that B is independent of M given A, and J and M are independent of E given A, and B is independent of E directly. Whereas these two guys are not independent. So the D-Sep condition will give you every possible kind of conditional independence assertion. And that's true semantics of the network.